Hello and welcome to your first lesson of 7th grade math. We're starting in Module 1, Lesson 1. This is all about an experiment with ratios and rates. Some questions that we're going to look at answering today is how can we determine whether a relationship between two quantities has a constant rate? How can we compare situations with constant rates? And what connections can we make between constant rate relationships and our knowledge of ratios from 6th grade? We'll start with a fluency activity. In my class, we do these in a composition book and we write our answers down each day. Typically, I give one example for students and then they complete the remaining problems on their own. So a trick that you may have learned when we're doing division is you can move the decimal the same number of spots in the dividend and divisor to turn those into whole numbers. Or you can think of this as how many quarters fit into 3 3/4. I'm going to show it with long division. So like I said, if I move it twice here, I can move that decimal twice there as well, which turns this into 375 divided by 25. Well, 25 fits into 37 one time. 7 minus 5 is 2. 3 minus 2 is 1. Then we bring down that 5. If we count by 25s, we're going to go 25, 50, 75, 100. 125 is the 5th one. So that would be 15. Because it leaves us with 0. Now we're going to watch a short clip on a coin sorting machine. Pay close attention to the details provided in the video to help us answer some questions that follow. We're going to use some cubes, some interlocking cubes, to pretend like we're sorting coins. Before we begin, we're going to predict how many coins you can sort by color in 10 seconds. I think that I can sort 20 coins in 10 seconds, or 20 cubes. Now we're actually going to give ourselves 10 seconds, and we're going to sort as many as we can, and then record how many we did. If you do not have access to cubes at home, you can use digital cubes on this website here. I've just placed a bunch on my screen and now I'm going to sort them, giving myself 10 seconds. So starting a 10-second timer. I was able to sort 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Doing this on the computer takes a little longer than I expected. So my prediction was that I could originally do 20, but it turns out that I was only able to do 9. I believe this should say predict how many cubes you can sort by color in 30 seconds because that's what we're going to do next. So since I was able to do 9 in 10 seconds, if I had 30 seconds, I would expect that I could do about 3 times as many, which would give me 27. Now I'm going to repeat this process, giving myself 30 seconds, and record the number of cubes that I can sort. I'll set a 30-second timer and begin. I was only able to sort 21 cubes this time. And I would record that number down here in part D. Now it says use these rates to complete the tables for machine A and machine B. Machine A sorts 20 coins every 4 seconds. Now I expect that a machine is going to have a constant rate, whereas myself sorting them, I did not have a constant rate. So if it takes 4 seconds to sort 20, then in half of the time, 2 seconds, I would expect to sort half as many coins. That would give me 10. If I started with 4 seconds and I moved to 8 seconds, I would expect to double. 4 times 2 is 8, so I would expect to double the number of coins that I would sort. 4 times 2 is 8. 20 times 2 is 40. If I went from 20 to 80, 20 times 4 equals 80. So I would need to multiply my time by 4. 4 times 4 is 16. Let's look for a pattern between 20 and 100. Well, 20 times 5 makes 100. So I need to use that same pattern to fill in the row. 4 times 5 is 20. Can you find a pattern between 4 and 12 to help you fill in the empty piece of the row here? 4 times 3 makes 12. So 20 times 3 will help us fill in this piece down here. Write your answer in the blank. It also says machine B sorts 33 coins every 6 seconds. Well, 6 times 2 is 12. So we need to use that same pattern to fill in this piece of the row. 33 times 2 is 66. We can also fill in this piece here. 6 times 3 makes 18. 33 times 3 would be 99. Now filling in the remaining might be a little bit trickier. I see that there might be a division pattern you can find. 33 divided by 3 gives you 11. So to fill in that same row, we need to take 6 and divide it by 3, which gives us 2. Now we don't always have to go back up to the first row. Now that we have this one established, we can use it to help us answer the remaining pieces. I can find a pattern between 11 and 44. 11 times 4 is 44, and 2 times 4 would help us fill in the seconds, which is 8. Let's see if you can do the last row on your own. How can I get from 11 and turn it into 22? use that same pattern to turn the 2 into the time. Then we are asked, does machine A or machine B sort more coins in 10 seconds? And explain how you found your answer. If we look back at the table, there might be several helpful rows to look at. We saw that 2 sorts 10 coins in 2 seconds. And then in machine A, they take 2 seconds to sort 11 coins. If we wanted to look at the seconds as 10 seconds, I can change 2 into 10 by multiplying by a 5. 2 times 5 is 10 seconds, and 11 times 5 gives us 55 coins sorted. If I do 2 times 5 here, that gives me 10 seconds, and 10 times 5 gives me 50 coins. The question was, which machine sorts more coins in 10 seconds? Machine A only sorts 50 coins in 10 seconds, but machine B sorts 55 coins in 10 seconds. So machine B sorts more coins in 10 seconds. And we have to explain how we found our answer. So we did 2 seconds for machine A sorts 10 coins. For machine B, 2 seconds, they can sort 11 coins. We multiplied by 5, and that gave us 10 seconds for 50 coins. And when we multiplied the seconds by 5 here, that also gave us 10 seconds, but it gave us 55 coins. So machine B sorts more coins. We're going to continue by looking at machine C and machine D. We might need to find a different type of pattern here. You can see that there are decimals in the machine D table. I can find a relationship between 8 and 2. 2 times 4 is 8. So what number times 4 gives me 36? 9 times 4 is 36, and 2 times 4 makes 8. So we use that pattern of multiplying by 4. Now we can use the row we just discovered to help us answer the next one. What number can I multiply 9 by that gives me 72? 9 times 8. So using the same pattern, 2 times 8 would give us 16 seconds. How about 9 and 2 times something equals 6? 2 times 3 is 6, so 9 times 3 will tell us what goes in this empty box. 9 times 3 is 27. See if you can find a pattern that would connect 2 to 14. What could you multiply 2 by? That would result in 14. Use that same pattern to help you fill in the empty section. Now let's look at machine D. I recognize a relationship between 9 and 18. I don't really recognize a relationship between these three numbers though. So let's start here. 9 times 2 is 18. So I can multiply 1.5 by 2 to fill in this missing section of the same row. 1.5 times 2 results in the number 3. I also recognize a relationship between the number 9 and 99. 9 times 11 makes 99. So let's multiply 1.5 by 11. 1 times 5 is 5, 1 times 1 is 1. Then we use that place value spacer as we move into the tens place. 1 times 5 is 5. 1 times 1 is 1. And we'll add all those together, giving us 165. But because there was one decimal place in the question, we also need 1 in the answer. So this would be 16.5. I also recognize a relationship between 3 and 12. 3 times 4 makes 12. So I can multiply 18 by 4 to get this piece of the row. 4 times 8 is 32. 4 times 1 is 4, plus 3 more makes 7. So 72 is going to fill in this section of the row. This last one is a bit trickier because I don't see a pattern or relationship between any of these numbers and 10. But I do have the ability to make these values even smaller. So let's work backwards and then build back up to 10. I know that 1 times 3 is 3. What number could I multiply by 3 that would give me 18? Well, 6 times 3 is 18. Now I can use this smaller row, or this smaller set of values, to build back up to 10. 1 times 10 makes 10, and 6 times 10 fills in this box. 6 times 10 gives us 60. So we had to do an extra step because there wasn't a quick, easy pattern to identify with the seconds that would get us to 10. So he built in an additional row to help us figure out this missing piece. So here I see that 10 seconds they can sort 60, 2 seconds they can sort 9. So let's use those values to help us answer the following question. So for machine C, in 2 seconds they sorted 9 coins. And for D, in 10 seconds they sorted 60 coins. Our goal is to figure out how many they can sort in 20 seconds. Well, 2 times 10 gives us 20, and 9 times 10, so this is the seconds, and they sort 90 coins in 10 seconds. To turn the seconds into 20 on this machine, 10 times 2 makes 20. So we use that same pattern of multiplying by 2. 60 times 2 is 120 coins. Therefore, machine D can sort more coins in 20 seconds. 120 is greater than 90. Now we're going to find what's called the unit rate. The unit rate is how much for one of something. We already discovered that machine D can make sort 6 coins in 1 second. We need to find the unit rate for the other machines. We can also find the unit rate for machine C, and we'll fill that in this box here. For 1 second, how many coins can they sort? In 2 seconds, they sorted 9 coins. So in 1 second, that is half as long, they can sort half as many coins. Half of 9, if we split 9 into 2 parts, would be 4.5. Another method you can use to find the unit rate is to divide the coins by how many seconds it takes. So here's an example, 36 divided by 8. Well, 8 fits into 32, that's 4 eighths. 36 minus 32 is 4, and there's an invisible decimal here, which is lined up, and we can bring down additional zeros. So how many 8s can fit into 40? That is 5 sets of 8 can fit into 40. So that's another way that we can get that unit rate of 4.5. Here we see machine A, B, C, and D. We already found the unit rate for machine C. 36 divided by 8 gave us 4.5. 9 divided by 1.5 would have come out to 6, but we already found that one a different way. Now let's do the first one. 20 divided by 4. How many coins per second? So we're going to do coins divided by seconds. When we say coins per second, that per is an indication to use division. 20 divided by 4 comes out to 5. Now we need to do 33 divided by 6. I know that 6 can fit into 33 5 times. 6 times 5 is 30. Forget about that decimal. 3 minus 0 is 3. 3 minus 3 is 0. Bring down another 0. 6 can fit into 35 times. So the unit rate for machine B is 5.5. Now we're going to complete the table using additional machines that we haven't worked with yet. Using that same method, coins per second, we'll calculate the unit rate. Coins divided by seconds. 42 divided by 6 is a unit rate of 7. 36 divided by what number would give us 6? We can work backwards to figure this piece out. 6 times what would give us 36? 6 times 6 is 36. Now for W, we're going to divide 27 by 4.5. Remember in our fluency, at the beginning of this lesson, we discussed how you can move the decimal the same number of spots to use whole numbers in your division. So now I'm going to use 270 divided by 45. That would be 45, 90, 135, 180, 80 plus 45, 225. And we're going to add another 45, which would be 270. So 45 fits in there perfectly with no remainders 6 times. So we're going to put a 6 here. Now we're working backwards again. If it's 10 per second, then in 3.5 seconds, we're going to multiply to work backwards. 3.5 times 10 would be 35. The coins per second, if it takes 40 seconds and they do 8 per second, in 40 seconds, 8 times 40 would be how many coins they can sort in 40 seconds. Well, I know that 8 times 4 is 32, so 8 times 40 must be 320. This one, 6.5 times something equals 52. So I can work backwards to figure out what goes in that empty box. Remember, this can be changed to 520 by moving the decimal 1 spot, and 65 by moving the decimal 1 spot. You could also count by 6.5 repeatedly until you get to 52. That's another strategy that you can use. So let's see here. If we counted up by 6.5, we would start with 6.5. 6 plus 6 makes 12, but a half and a half would make it go 1 higher to 13. 13 plus 6 makes 19, and then we have that extra half. 19 plus 6 would make 25, but we have the halves, which is going to make it go up to 26. 26 plus 6 makes 32, plus the extra half. 32 plus 6 would make 38, but we have 2 halves, making it a whole of 39. 39 plus 6 would be 45, plus the extra half. 45 plus 6 would be 51, but we have that extra half, making it 52. So that's 1, 2, 3, 4, 5, 6, 7, 8. You may notice that machine V and machine W have the same unit rates, and at these different times, they've completed different numbers of sorted coins. So the longer the machine runs, the more coins it can sort, but they still had the same unit rate, meaning they're sorting the same number of coins per second. Noor and Eve are looking for a new coin sorting machine. They see a machine that sorts 10 coins in 4 seconds. Noor says the unit rate is 2.5, but Eve says the unit rate is 0.4. How can we determine who is correct? Remember, to find the unit rate, we want the number of coins per second. That means that we'll take the number of coins, which is 10, and divide it by the number of seconds. 4 fits into 10 2 times, giving us 8. Don't forget about those decimals. 10 minus 8 is 2. Then we bring down one of those invisible zeros, and 4 fits into 25 times, because 4 times 5 is 20, which means Noor is correct. If we look at these 4 tables, we're going to determine which of these tables sorts the coins at a constant rate. So a constant rate occurs when the unit rate on each row is the same. So if we start the coins per second here, 12 divided by 2 would give us a unit rate of 6. But in the next row, 5 seconds and 40 coins per second, 40 divided by 5 is 8. Those are not the same, so this is not sorting at a constant rate. Let's look at H. Coins per second, 21 divided by 1, 42 divided by 4. 4 fits into 4 once, giving us 0. Bring down the 2. 4 doesn't fit into 2, so we put a 0 at the top. Bring down another 0. 4 fits into 25 times. Well, 10 and a half is not the same as 21, so this is not sorting at a constant rate. Here, if I divide 4 by 2, 4 divided by 2 is 2. But 16 divided by 7 is not 2. So machine I is also not sorting at a constant rate. How about machine J? Coins per second. 24 divided by 3 is a unit rate of 8. 40 divided by 5 is also 8. And 56 divided by 7 is also 8. So machine J sorts at a constant rate of 8 coins per second. In order for something to have a constant rate, it must do the same amount every second. So how can we determine whether the machine sorts coins at a constant rate? We look at each row and determine if all the rows have the same rate. To compare situations that have constant rates, we can look at their unit rates and determine which one is more or less. What connections can we make between constant rate relationships and our knowledge of ratios? Well, we use the ratios but we turned them into one of something. So those rows were ratios, and a unit rate is when we had 1 second as part of our ratio. Check back for lesson 2 from module 1.